Okay, so the third speaker of this session is Tatiana Brailovskaya from Princeton University. So take it away, Tatiana.
Yeah, so first I'd like to thank the organizers for allowing me to give this talk. And today I'll be talking about the work that I've been doing with my advisor, Banderian Manhandle, on the eigenvalues of inhomogeneous random matrices. So first, I would like to start by talking a little bit about the types of random matrix models one might be interested in studying. So first, there are the classical random matrices, which are highly homogeneous, these Wigner type matrices where we have IID entries and they all typically have the same variance. And so for simplicity's sake, they all have unit variance. And these objects have been a while for quite a long time and they've been studied at length and we know a lot of things about them. For example, since this talk will be about the largest eigenvalue, I'll mention a result about this in this context. In particular, if we make some assumptions on the moments of the entries, we can show for these Wigner matrices, the largest eigenvalue are scaled by square root of the dimension converges to the constant 2 almost surely. And we actually have a lot more information about these objects, but I will not get into that. But of course, as you can imagine, there are lots of other different kinds of random matrix models that might be of interest to theoretical physicists or applied mathematicians. And very broadly, I'll call them structured random matrices. And of course, there are many, many examples here. I'll just give you a couple so you kind of get a sense for what types of models these are. One example would be, say, a sparse Wigner matrix. And these are random matrices that have a fixed sparsity pattern, meaning we set certain entries to have 0 variance, and then the rest are just going to be IID. And already something like this is not captured well by any of the classical theory. Another example would be the Gaussian series, where we have some collection of deterministic matrices, and then we take linear combinations of them, where the scalar multiples are just IID standard Gaussian variables. And finally, the model that I will focus on today is a Gaussian random matrix where the entries are independent. However, unlike in the Wigner case, here we'll allow the entries to have arbitrary variance patterns. So let me be a little bit more precise about the model. So we'll be studying these Gaussian random matrices with independent entries, such that the ijth entry above the diagonal will have the distribution of a Gaussian with mean 0 and variance bij squared. And then on the diagonal, the entries will have variance, or they'll have a distribution of a Gaussian with mean 0 and variance 2 bii squared. And I mean, this 2 here maybe looks a little bit weird, but it ends up being sort of like helpful for proofs, but it doesn't in any way reduce the generality of our results. And I would like to also mention, I guess several people have brought up this classical random matrix object, but I'll just define it again. The Gaussian orthogonal ensemble, or the GOE matrix, is a symmetric Gaussian random matrix such that above the diagonal you have IID standard Gaussians, and on the diagonal you have Gaussians with mean 0 and variance 2. And as you can probably notice, that this is just a special case of this more general model that I've defined for you here if we just set the Bij parameters all equal to 1. So I would like to now talk a little bit about some tools and techniques that sort of already exist in literature to deal with these types of objects. And in particular, I think until fairly recently, the most common inequality to deal with these kinds of inhomogeneous random matrices has been the non-commutative Khinchin inequality. And it applies in a slightly more general setting than what we have here, but I'll just specify the relevant results. So when we have this Gaussian random matrix with independent entries, we know that the largest eigenvalue is going to be bounded above by this parameter sigma, which I've defined for you here, times square root log of the dimension. And this inequality holds up to universal constants. That's what this squiggle notation means, if you haven't seen it before. If you haven't seen this inequality before and haven't thought about random matrices, it might seem kind of like a strange inequality. It's hard to know if this is good or bad. How useful is this? So in order to get a better understanding, let's consider a couple of simple examples. So the first example we're going to look at is the GOE matrix, which I've already mentioned. From classical random matrix theory, we know that the expectation of the largest eigenvalue of a GOE matrix behaves like 2 times square root of the dimension asymptotically. So now let's plug this into the non-commutative Khinchin and see what we get. So first, I'll calculate the sigma parameter, which in this case is simply square root of the dimension. So now that we plug this into the inequality, we get that the non-commutative Khinchin gives us a bound of square root of the dimension times log of the dimension. And of course, this is a valid upper bound. There's no contradiction here or anything, but we can see that there is this extra square root log of the dimension multiple, which makes this not sharp, which means the non-commutative Khinchin inequality doesn't quite capture the behavior of the GOE matrix. Now let's consider another example. let's look at X, which is a diagonal random matrix with IID standard Gaussian entries. And again, this is another sort of very simple case where we can explicitly calculate the expectation of the largest eigenvalue. And in this case, we know that it's equal to square root 2 log of the dimension. Now let's see what the non-commutative inequality will tell us in this case. So the sigma is just a constant. And so we exactly get that the upper bound should be square root log of the dimension. So to quickly summarize, we can see that the non-commutative inequality performs well when we have the diagonal random matrix, but it fails to capture the GOE case. And well, one might wonder, if these are two sort of very canonical examples of random matrices, is there a nice inequality that kind of is more general and is able to capture both of them? Because it seems like that's a reasonable goal to be able to have a general theory that describes the behavior of the spectrum of both of these random matrices. And in fact, this is possible. This was a result proven by Banderian Manhandle in 2016. And they showed that for this, again, the Gaussian random matrix with independent entries, the largest eigenvalue is bounded above up to a universal constant by the same parameter sigma as we had in the non-commutative Kenshin, plus sigma star times square root log of the dimension, where sigma star is another parameter that I've defined for you here. So the first thing to observe here is that this quantity that we have on the right is smaller, again, up to universal constant than what we had in the non-commutative Kenshin case. So this is already a dramatic improvement. But furthermore, the important thing here is that it does actually properly capture the asymptotic behavior of the eigenvalues of the GOE and the diagonal matrix. So let's just briefly review. So I already told you that the expectation of the largest eigenvalue of the GOE behaves like square root of the dimension. And if we plug this into this new inequality of Banderian Manhandle, we get that the largest eigenvalue should be bounded above by square root of the dimension plus square root log of the dimension. And of course, as the dimension goes to infinity, the square root term will dominate, and we recover the correct asymptotic behavior, which we weren't able to do before with the non-commutative Kenshin. And we can also see that the same thing happens where we're in the diagonal setting, where we have that the largest eigenvalue behaves like square root log of the dimension, and that is precisely what we get from the results of Banderian Manhandle. So this is already a pretty amazing result, and perhaps there's one place where we can improve it, which is that one might ask, can we remove this universal constant and actually figure out what exactly should be the numerical constants in front of sigma and sigma star, and preferably can we find such constants that are optimal? And this is the work that I did with Banderian Manhandle, and this is what we got. We have that the expectation of the largest eigenvalue is bounded above by 2 times this slightly weird looking quantity, which is a little bit different from what we had before. But if you look at it carefully, you can see that this is basically the same thing as just sigma, unless we're in a situation where sigma squared over sigma star squared is not an integer, but then it's still basically approximately sigma. And then the second term is just 2 times what we had before, sigma star times square root log of the dimension. So I claim that these constants are actually optimal, that we cannot improve them, meaning that we can't prove this inequality with, say, like putting a 1.8 instead of the 2s or something like that. And as you may have guessed it, again, we can demonstrate that these constants are optimal by plugging in our sort of 2 favorite canonical examples of a GOE matrix and a diagonal matrix with standard Gaussian entries. So I would like to now very briefly mention what sort of techniques we use and what is sort of our idea for the proof of this fact. And the first thing that we did is we developed this moment comparison inequality, which basically allows us to compare moments of this like highly inhomogeneous random matrix of interest that, of course, we don't really know how to study, to the same moment of a GOE matrix of a particularly chosen dimension. And of course, a GOE matrix is very well understood. So now we can use some basic facts about these matrices and some concentration inequalities to arrive at the bounds on the eigenvalues that I was showing to you on the previous slide. Yeah. So that's all I have. Please let me know if there are any questions.